The forest for the trees. Decision trees are transparent, intuitive, unstable, and unreliable. So we tend to create forests, random forests of decision trees. So decision trees are based on information gained at the nodes. They're defined recursively. You partition at previous level, defines populations at the next level, and then you end up with these conditions, these decisions, and which is the best decision is based on information gain. Your goal is purity. The information gain is often interpreted as a measure of impurity, and then there are other measures of impurity, for instance, the Gini coefficient. To make predictions with decision trees, you have a prediction function f of x. And what I mean by that is you do this information gain, you get best decisions, you split the data, and then you repeat. So this is the way we form the tree. And then the leaves give us the results. Our prediction function, if we have x as some test point or unlabeled observation, then the decisions are made in the leaves. And f of x is based on whatever the leaf data is. So if I've got a test observation or an unlabeled observation, then once I get through the tree, I use the leaf that I end up with as a prediction of whatever that observation is. For example, if we had two classes in each leaf and we ended up in this leaf, then we would say f of x is 0.8. Bayesian confidence of 0.8 that it's positive. The decision trees are often unreliable. So we randomly generate a forest of trees, a random forest. Given training data, observation plus the response of size m, for b equals 1 to capital B iterations, we sample with replacement, m training samples, that's bagging. We train a decision tree with the resampled data. We use a random sample of the features at each node, and we produce a function f sub b of x, which is a decision for a test point x. And then we make a prediction from the forest, which is the average over the individual decision tree decisions. There's a lot going on here. This is an ensemble method, and we're using bagging, and we're doing feature bagging when we do a random sample of the features, and we are doing an ensemble average. So just briefly, why do these random forests work? Well, here is a brief overview of our algorithm. For some number of iterations, we do bagging. And then for each node in the tree, we do feature bagging. And then we have ensemble averaging. Bagging gives us stability and reliability. It's bootstrap resampling. And it models the concept of having multiple training sets. So from one training set, using sampling with replacement, we have, in some sense, many training sets. Feature bagging is a random subspace method. We don't want to create B identical trees. So we want to reduce the correlation among these B trees in the random forest. And this, of course, is what's known as an ensemble method. So let's look at an example, the Wisconsin breast cancer data set. This has two classes, malignant and benign, 9 features for each patient, each feature being a rating ranging from 1 to 10 of these clump thickness, uniformity of cell size, uniformity of cell shape, so on and so forth. So here is what our data looks like. There's 699 observations, and there is missing data. So I'm going to defer imputation to a previous lecture. In other words, we're going to use imputed data. So here is our imputed Wisconsin breast cancer data. And we're going to create a Y, a response, which is the class, 1 for malignant, 0 for benign. And then we're going to create a random forest. And it's very straightforward how you create a random forest. So there are many options. And then we fit and score, and we get an accuracy of 0.942857. And we get a pretty nice looking receiver operating characteristic and area under the curve. Now the key here is that each one of these random forests contains a whole bunch of trees. So if we look at the scores and the trees, then we end up with the ability to have the highest scoring tree in the forest. So all the trees in the forest, each tree scored on the test data, sort it by accuracy score, and what do you get? You get a collection of the best trees in the forest. So we're going to look at these individually. So first off, let's look at the very first tree. This was the best scoring tree, and it looks something like that. Well, that's pretty impractical. It's too deep. So it's got great scores, but we better revisit the possible options. So here are all these options. Notice one of the options is depth, and another one is the minimum samples in each leaf. In this case is 1. So we're going to rerun our random forest with a maximum depth of 4 and at least 10 observations in each leaf. So once again, we get a pretty good receiver operating characteristic. We get a good accuracy score. But now we get trees that make some sense. The 10 best scoring trees are here, and notice that the top 3 I've drawn for us. Here's the best scoring tree, and notice that it becomes diagnostic. So we can actually say how to diagnose somebody based on the values of these features. So suppose we had a patient that had these results in their biopsy. Clump thickness 8, size uniformity 10. You can see the numbers there. Well, bare nuclei is the first decision, and then we get to clump thickness, and then shape uniformity, and bare nuclei again, and we have a patient that's been predicted, unfortunately, malignant with probability 1. Here's another patient, bare nuclei 10, and clump thickness is 2 in this case. Now we get to shape uniformity, and we end up in this leaf. And in this leaf, the patient is predicted to be benign with a probability, a Bayesian confidence of 0.89. But you got to be careful here. This was only based on a subset of the features. Each tree only uses a subset of the features. So we don't have correlation between the trees, but we still have instability in individual trees. So what we need to do is look not at just one tree, but at all the trees. So here's the second best scoring tree, and here's our second patient again. Notice this time they're going to end up going in this route, and now they're predicted to be malignant with a probability of 0.8667. Remember, in the previous, they were predicted to be benign. So you should use all the high-scoring trees when you use a random forest diagnostically. Here's the third best scoring tree. Okay, so again, you want to use the forest to make a prediction, not just a single tree. So notice, in this case, patients predicted malignant with this probability. So random forests are actually universal. A decision tree partitions the data among its leaves. Its prediction function, therefore, is constant on each leaf. In other words, its f sub b of x is piecewise constant as a function of x. A random forest prediction function is an average of piecewise constant functions. What did we learn in calculus? Well, any piecewise continuous function can be approximated by an average of these piecewise constant functions. So here's an arbitrary continuous function, and here is its piecewise constant approximation. So random forests are also related to nearest neighbor methods. In general, a weighted neighborhood scheme for data t sub I, y sub I equals 1 to m is a scheme that predicts a label for each x via y hat is the sum I equals 1 to m w of t sub I comma x times y sub I, where these w of t sub I comma x greater or equal to 0 are the weights of the weighted neighborhood scheme. For example, in k nearest neighbors, this weight w of t sub I comma x is 1 over k if t sub I is a k closest neighbor of x and 0 otherwise. For a decision tree, w of t sub I comma x is 1 over L if x and t sub I are in the same leaf and that leaf has size L, and w of t sub I x is 0 if x and t sub I are in different leaves. For a random forest, we take an average over the trees, and we can rearrange the sum in which we see that the weighted neighborhood scheme for a random forest is an average over the weights for the trees. So ensemble methods go beyond intuition, but certainly intuition works. Using more trees and in general more than one classifier at a time is intuitively advantageous. Also advantageous in reality. So addresses weaknesses in individual classifiers, reduces uncertainty via separate individual processes. Speed may be an issue. More classifiers means you're going to do a lot more computation. And not surprisingly, there are other things besides random forests. There's the extra trees classifiers, gradient tree boosting, all have this advantage of more trees.